Hello guys, welcome to another tutorial on PHS 105, and today we are treating heat. Yes, heat. What is heat? Heat is actually that energy that carries temperature. That energy that carries temperature from one body to another. It's just that energy that is transferable. Heat is energy that is transferable, energy in form of temperature that is transferable. Yeah, and today we are focusing on the types of heat we have. Types of heat capacity. Now, before I continue, heat capacity is actually the ability of a body to accept heat, the capacity of a body to transfer heat. That's heat capacity. It's as simple as that. But we are not all about the definition, we just want to know how to calculate, isn't it? Okay, so what are the different kinds of heat capacities? Now we have the specific heat, and we have the latent heat. Now, what is specific heat? Specific heat is the kind of heat that causes increase in the temperature of a body. Increase in the temperature of a body while the state remains the same. So, if the temperature of water, for example, now, if water goes from 0 degrees Celsius to 50 degrees Celsius, what has happened here is just the specific heat. So that's what specific heat is. Heat that increases the temperature of a body without changing its state. Now you should have the idea of latent heat. Now the temperature remains same, but there's a change in state. The temperature remains the same, but there's a change in state. So if water goes from 100 degrees Celsius to steam, it is still at 100 degrees Celsius, right? But it has gone from water to steam. So the heat responsible for this is called the latent heat. You have to know heat capacity of water. You have to know it. Though it might be provided in the exam, fine, but then you have to know that of water. For the rest, you might be provided, you will, but for water, you have to know it. So let's just quickly deal with that. Now, what is the specific heat capacity of water? Specific heat capacity of water equals to 4,200 joules per kilogram per Kelvin. You have to know it. Remember, I said physics is all about knowing the formulas. Now, specific heat capacity of ice is still water, right? Of ice, 2100 joules per kilogram per Kelvin, and the latent heat of fusion. Latent heat of fusion of water is 336,000 joules per kilogram per Kelvin, and the latent heat of vaporization, that's conversion of water to steam. This is conversion of water to ice. That's fusion. Fission is conversion of water to steam. Is 225,000 joules per kilogram per Kelvin. Okay, so you have to know this. Now what does this value mean? This value means that it takes water, it takes 1 kg. It takes 1 kg of water, 400 joules of energy to be increased by 1 degree Celsius. I don't know if you are getting me. Now let's assume this is 1 kg of water here in this cup. This is 1 kg of water inside this cup. Now I place it on fire here. Now for this, and let's assume the initial temperature T0 is 30 degrees Celsius. Now I placed it on fire and it went to 31 degrees Celsius. Now this 1 kg of water, for it to have moved from 30 degrees Celsius to 31 degrees Celsius, it took it, you guessed right, it took it this amount of energy. This is the amount of heat energy it took 1 kg of this water to move from 30 to 31 degrees Celsius. So now and I think something should come to your mind with that, the definition. Something should come to your mind with the way I've explained. Meaning that if it goes from 31 to 32 again, now that is another what? Another 4200. So if it goes to 32. Now if it goes to 33, that's another 4200. Now you should already have that picture in mind that okay, that means if you want to know the amount of energy it will take for water, that's 1 kg of water to move from 40 to 50 degrees Celsius. If you want to know the amount of energy it takes, it means that, let's first subtract this to know the difference, isn't it? So that's 10. It has 10 different. That means 10 times. It's this. You have 4200 10 times. So that means it took this energy for 1 kg of water to move from 40 degrees Celsius to 50. You understand that, isn't it? Okay. So the formula is coming to play here. And what is the formula? The specific to calculate the heat energy required for any body. It's not even water this time around. Anything to move from one temperature to another temperature is actually a matter of its mass. Remember that we've been talking of 1 kg since. So that means if it is 2 kg, you must consider its mass. That means 2 kg means 2 times of this originally. Okay, before I go to the formula, okay, we've done for 1 kg. Now what of if the mass is 2 kg? It means if it is 1 kg, that means it is consuming this amount to move one temperature higher. So if it is 2 kg, that means it will consume double of this amount to move one temperature higher. Sorry, let me see if I can do an illustration. So this is a cup of water. Don't mind me, I'm actually an animator, so I believe illustrations would help you guys understand better. Okay, so this is a cup of water and it contains, this is 1 kg and this is 2 kg. 2 kgs. Okay, now if I place this on fire now, according to what we said, for it to move from 30 to 31, it takes, like we said, it takes heat energy of 4200. That's what we said. Now this, remember, this is 1 kg. Now if we are doing the same thing for 2 kg, it is normal. This is physics, it's about quantities. We believe that if 1 kg takes this, that means 2 kg should take 2 times double of it. So it means 2 kg, for 2 kg to move from 30 to 31, it means that it has to take this one 2 times, because 2 times because of the size. Okay, now having said that, so it means that the mass of that object must multiply the heat energy, and at the same time must multiply the amount of times the temperature increases, the change in temperature. So that means there's a formula coming to mind now. Since that means the formula to calculate any heat is the mass of that body must multiply its heat capacity. Its capacity is written as C, small c, and must multiply its change in temperature. Boom, we've gotten the formula of specific heat capacity of any substance. So the formula for specific heat is mc change in theta. Now the formula for latent heat is mL. There's no change in temperature, since latent heat doesn't actually change temperature, it's only change the state. So I believe this is well understood. Yeah, it is. Let's treat a question. Like I said, okay, you should be able to get questions like this in exam, but then some other questions you get might be a little bit thicker than this. So I believe we understand simple questions on this, but let me treat a conk one just because of time. Okay, now heights at 0 degrees Celsius is heated till it reaches water at 100 degrees Celsius. Calculate the heat required for the conversion. Now, this question is tricky. Yeah, it is, because this time around ice has gone from 0 degrees Celsius to water at 100 degrees Celsius. It's actually, we can say okay, since there's a change in state, there isn't latent heat, but this time there's a change in state and there's also a change in temperature. Remember, latent heat is about change in state, but no change in temperature. But specific heat is about change in temperature, no change in state, isn't it? But this time there's a change in state, there's a change in temperature. But in order to solve this very well, you have to break down all the steps that happened. Now, for ice, how should ice go? Ice should go from ice at 0 degrees Celsius. It must melt to water at 0 degrees Celsius, isn't it? It must melt first. Now, if it melts, then it can now go from water at 0 degrees Celsius to water at 100 degrees Celsius. So this is actually what happened in between there. So you have to calculate the heat energy required for these two steps, then you sum it together. Now we've broken it down. Now ice at degree Celsius, 0 degrees Celsius, water at 0 degrees Celsius. That should be the first thing that will happen. The ice must first melt, but the temperature will still remain the same. Okay, so now for this one, you should have guessed like that. This one is the latent heat, and this one is the specific heat. So for the latent heat, now let's quickly solve it. The H for latent heat is ml, remember? So mass, oh, I didn't put the mass of, let's say 20, or let's say 2 kg ice. Yeah, so we already know that the mass is 2 kg. And what is the latent heat of fission, that is conversion of ice to water? 33600 joules per kilogram, 00 another 0 joules per kilogram per Kelvin. So it is 2 times 336,000, and that's 0.00276. So that this is it, joules. This is the answer, joules. Okay, yeah, that's it. Now that's for latent heat. Now let's go to the next one, which is the specific heat. Now water, that specific heat equals to mc change in theta. So m, we already know that m is 2 kg. C for water, what's specific heat capacity of water? Specific heat capacity of water is 4200 joules per kilogram per Kelvin. Then we already know that the change in theta equals to T2 minus T1, or whatever you use to label your own. 100 minus 0, then 100, change in theta. So H equals to m 2 times 4200 times 100, 200 times 4200, that's 84000 joules. So all you just need to do now is add two of them together, and that should be 67200 plus 840000. So the answer should then be 000 2 1 So this should be the answer, I guess. Just confirm it. I don't know, I just did a rough calculation. So this should be the answer. So it's as simple as that. And I know some of you might be asking, what if you have something like this? 2 kg ice, 2 kg ice super cooled from minus 20 degrees Celsius, then it was heated until it reached steam at 100 degrees Celsius. Now how do you calculate this? So this one is actually simple, just like what we've done before, but it's just that it has many processes. Now firstly, the ice has to go from minus 20 to 0, isn't it? The ice must cool down first to what it should be now. So minus 20 to 0, that means ice at minus 20 degrees Celsius must first go to ice rest. Now this one is specific heat. I hope we know, because the state is the same, but there's a change in temperature. Okay, now highs will then go from this highs at 0 degrees Celsius will now go to water. It will melt, but still at the same temperature. Now this is what the latent heat. Now water at 0 degrees Celsius will first boil. It will first boil to water at 100. Now water, after it has boiled, that's when it will now start vaporization. Sorry, vaporization is different from evaporation. This after it has boiled, then it will now start going to steam. So this one is latent heat. So just use the same. Once you've listed everything out like this, you can then work it out. So that is that for heat. That is that for heat and heat capacities. So I implore you to know the various this. Please know this. At least for this ones, know. The rest should be given to you, but for this one, you know. And the question comes in different ways. The question sometimes come in a very funny way, that you have to find the heat. I wish I could. Let me see if I can still spare a little bit of time to bring one more question. So you might be told that 4 kg iron at 100 degrees Celsius was poured into was dipped into water, into 1 kg water at 20 degrees Celsius. Find the resulting equilibrium temperature. Find the resulting equilibrium temperature after heat has been transferred. So after it has been transferred, find the resulting equilibrium temperature. Okay, now we know, I hope we know that if two bodies touch, the reason why you can, I believe, I think I should cover this in another topic. The reason why you feel that another person is hot is because your body is cold. That's why you can feel that another person is hot. That's why sometimes when you touch somebody, you might feel that a person is hot. Another person comes around and you feel like this person is also normal. Maybe this person feels cold. It all depends on the temperature of bodies at the moment. So what am I trying to bring out? The one with higher temperature always transfers heat to the one with lower temperature. That's why, like I said, you feel that somebody is hot because the person is hotter than you. It's transferring the temperature to you so that you can feel it. Or the person will feel that you are hot and you feel the person is cold because your body is transferring the temperature to the other body. So when this iron, according to the question, if this iron is dipped into water at 20, the iron has higher temperature than the water. So it is expected that the ion loses temperature to the water, isn't it? But after some time, there will be this point where you won't feel anything anymore. As if you keep touching the person, you place your hand there for a long time, it feels normal for the two of you. As the two bodies have reached equilibrium, there's no heat transfer again, because the same amount of heat is the same. The amount of heat on one side is same amount of heat on the other side. So now find the resulting temperature. It's actually the same because there must be heat transfer. So that means the heat gained by one body is the heat lost by the other body. So H of one body gained is H of the other body lost. So that means MC theta, change in theta of one body should be the MC change in theta of the other body that is losing, isn't it? So basically that's it. Then we can now go on, but you have to be careful. You must know the body that is losing heat, you must know the body that is gaining heat. So since iron is the one losing heat here, so you must place it where it should be. And though it doesn't matter on which side of the equation, it might be here, it might be here, what matters is how you place their temperature. That's the important thing. And so let's try it. So let's say I can place iron anywhere. Let me just follow my formula here. Since this is gained, this is lost. So gained, water is gaining. So this is 2 water. The mass of water according to here is 1 kg. The mass of iron according to here is 4 kg. So mass of water here, that's 1 times, we know the specific heat capacity of water, times the change in temperature. It is gaining heat. We have to be careful with this. Water is the one gaining heat, so its temperature is increasing. So that means 20 here should be the least of its temperature. So that means this one, temperature 2, is what we don't know, minus temperature 1, 20 degrees Celsius. I believe we understand that since it is the one gaining the heat, so that means 20 should be the smallest heat that it should have, since it is the one gaining. So the temperature must be in front. It is very important you take note of this. Now iron is on the other side, 4 times. Right now I don't remember its capacity of iron. So let's just say capacity of iron, whatever it is, just put it there. The point is you understand where the temperature, how to place the temperature so that you can get the answer. Or let me just assume that, let us assume, that's a warning, assuming the C for iron is 100, assuming. Okay, so let's assume $100. Okay, now times, now iron is the one losing heat, so that means 100 should be the highest temperature it can have at this time. So minus theta 2. Now why did I put it as theta 2? Because at point of equilibrium, these two will have the same temperature. At the point of equilibrium, these two will be the same, and it is that point of equilibrium we are trying to get. So these two should be the same. It doesn't matter what you use. You can use anything. You can use theta. You can just make sure they are the same. That's the point. So you can then continue solving. So just simplify, expand, get your theta to bring them to the same side, and so that's just it. So equals to 4,000 plus 84000. So the rest is just simple mathematics. Just break it down and get your answer, and that's just it. That's it, guys. That's it. So that's it. This time I mean that's it, not that's it. English and voila. So that's basically it, guys. That's it, and that is it. So we continue another time. Please don't forget to subscribe. Support my channel by subscribing. It will do me a whole lot. Thank you very much. Peace.